My name is Joseph Anderson. I'm the Executive Director for the Steel Tube Institute, and you're in the session, What Your Fabricator Wishes You Knew About HSS. Before we get started, those who are on the broadcast, if you'd like to send in questions, send them to nascccroom2@gmail.com, and the moderator will include your questions into the question and answer session following this presentation. Kim Olson is a partner in Force Consulting and is the technical advisor, consulting engineer to the Steel Tube Institute. She's been on board with the Steel Tube Institute since 2012 and currently serves as that consulting role. She'll be making the presentation this afternoon, so I'll turn the time over to her.
Good afternoon, everyone. Hope everybody is refreshed after lunch. Like Joseph said, my name is Kim Olson. I am a consulting engineer with Force Consulting. We are the technical consultants for the Steel Tube Institute. So I do a few technical presentations, answer some questions, and basically do any structural engineering that they need. A little bit of my background is I started my career in Denver. I worked there with Martin for 7 years doing project work. I then moved to the Philadelphia area and worked with Bentley Systems working on the RAM software. Was there for a few years and then jumped back more to the consulting side, and that's where I am now with Force Consulting, where about half of my work is with the Steel Tube Institute and the other half I still do a bunch of project work as well. So real quickly to get started, there's a true or false question that looks like some of the formatting is a little bit messed up, that I'd like to get your opinion. And so it's a bit of a trick question, so I'll warn you up front. But just by a raise of hands, who thinks that this is true? HSS structures in general are more expensive than those made up primarily of wide flange sections. True? All right, how many think that's false? So almost evenly split, not bad. All right, so I warned you that it is a trick question because you can't really ever make that generalization. It's not fair to just try and say that they're always more expensive or they're always less expensive. And the reason being is because there's a lot of factors that obviously weigh into that statement. Starting out with the material, how are you using the tubes in question? So if you're using them as columns, it's common perception that HSS is going to be more expensive, but actually when we compare a column to a wide flange, if you look at the cost of it these days, actually pound for pound they're pretty equivalent, which is unfortunate for my producer friends. That's not always the case, but almost always in every case, because of that lack of a weak axis in a tubular section, you're going to get more efficient use out of your steel and out of your money, and it's going to be more economical if you do choose a tubular section rather than an open section. Now, beams are a whole different story, right? I'm not going to stand up here and tell you to use HSS beams because we always know that every day and twice on Sunday, wide flange beams are going to be more economical than tubes. Unless you have a condition where you've got biaxial bending or you've got some torsion being induced into that beam, then obviously that may be a better case for using a closed section. But you're probably going to want to always stay with a wide flange section if you're looking for your most economical section, or system, sorry. And then when it comes to fabrication, so that's, thinking about one piece of it, which is just the material. When we talk about the fabrication, fabrication is expensive. There's the thought process or the feeling out there that fabrication when it comes to HSS is always expensive. It's very expensive. It's going to be more expensive than in using open sections. And that's not always the case. It is sometimes the case, but what I've found is that really tends itself to go towards details that are not well thought through, or maybe specifying one detail to cover every condition on a job. And we'll talk about some of those conditions as we get through here. So what I want to start with is that we need to think through all of these details. Even though some of the material may be more efficient in using HSS, if we don't think about the details and the fabrication side of that, all of that that economics can be thrown out the window if we don't think through them. So why are we even talking about this? So as a consultant with the Steel Tube Institute, the number one complaint that I hear about why people don't want to use HSS is because they say that it's expensive. So then I started wanting to drill down in that, because I know that material-wise, that's not always the case, that a lot of times a closed section is more economical than some of the other options. So then I start hearing about connections. Well, connections are hard to design. There are not enough resources out there. So we've been working on that as well. But going a little bit further, we've heard that there are fabricators that don't like to do HSS projects, or their feeling is that they're very expensive. And so what I really wanted to do as a structural engineer is to kind of get some input from a fabricator, because I obviously don't live in that world. I wanted to know more about what are we doing as engineers that cause these fabrication costs to go up so high. So what we did with this Steel Tube Institute is we had a spring meeting. It's almost a year ago now, and we invited these 5 fabricators that you see listed here. AISC recommended them to us. They range in shop sizes from smaller shops to larger shops, and they also cover both or all corners of our country. So hopefully a good representation of what we all deal with across the U.S. In addition, I also had some help from Joe Tibbin and Bill Zimmerman with Zimcor. They've helped me because they're local to Denver and they do a lot of HSS, so they also gave me a bunch of input for this presentation. Just want to thank those people. And that's where a lot of this information came from. They're all AISC certified fabricators. So starting with shear connections, that was the number one topic, and we spent a bunch of time on this. Here you're going to see 4 details for shear connections. They're all going to be wide flange beam to HSS column, and these are listed from least to most expensive. So starting with the least expensive would be if I had a shear plate or a shear tab connection. Just weld that to the face of the tube, maybe bolt or weld it to my beam, and go about my business. This is always going to be the least expensive and most economical option. If that doesn't work for me, I can also go to a WT connection where I'm welding twice to the tube and then bolting to the beam web as well. And then next I can look at a double angle connection. So this is a little bit more expensive, get a little bit more capacity out of it. What you need to think about with these double angle connections is the width of the column. I obviously can't put 2 angles on an HSS 4x4 column, so I need to have a wider column if this is the type of connection that I'm going to specify. Like is shown in this diagram, I've got a rectangular column with a wider face that I can use that double angle connection with. We also, unlike what's shown in my sketch, there would be some coping required for erectability, that you may need to double cope this beam in order to be able to erect it efficiently. And lastly, and most expensive connection is this through plate connection, where you actually slot the tube on 2 faces and pass a single plate through the slot, and then you can weld the plate to the tube walls. So you actually get 4 welds on a through plate. So of these 4, only 2 of these you can use if you've got circular columns. I've shown rectangular columns where you can all use them, but if you've got circular columns, obviously the only 2 options you have are that single plate and the through plate connection. So the through plate, research has found that it's 4 times more expensive to specify a through plate connection. I thought, as an engineer, that we had kind of moved past the through plates, that nobody's really specifying them anymore. We've kind of, only specify them when we absolutely need them. But in talking to these fabricators, evidently there are a lot of people that are still specifying them. They are still showing up as kind of your standard connection detail that gets passed from drawing set to drawing set. Whenever you have 2 columns, you go ahead and put that guy on there. And it's really, really, really a very expensive connection. So we want to try and avoid it at all costs. In fact, if it takes bumping up your wall thickness on your column, like if you've specified a 3/16 inch wall and you're going to end up with a through plate, it's going to be more economical for you actually to go and specify a 1/4 inch wall to avoid having to go through that through plate connection. A couple more things that they brought to my attention that I thought were interesting is that if we look at like this type of connection here where I've got a single through plate going through, this actually, one single plate going through in one direction actually requires a full extra hour of shop time. So you can imagine if this is my typical connection on a structure that has 40 or 50 of these things on it, how much extra time is being built up because I've specified this as my standard connection, and how much money I can save the project by going to a single plate connection. Something that was also interesting that I wasn't aware of after talking to these fabricators is that there are some people that maybe aren't watching their weld symbols and they actually put the all-around symbol, and whether they meant to or not, they actually required the fabricator to weld on the inside of the tube, to weld that through plate on the inside of the tube. No joke, it's happened. And so what they ended up having to do is they literally had to chop off the top of the column so that they could get in and make that weld of the through plate to the inside of the tube and then weld the column back together. Obviously, not the best idea. Along with that, that same fabricator also showed me an example of a condition where someone had specified through plates in two directions. So again, the fabricator had to cut the column in half because there are through plates. Again, it was just there. I mean, I can understand if it's your standard connection, you don't think you've got beams coming in both directions, you just didn't think about it, right? Maybe? So the fabricator had to lop off the top of the column, get those through plates in a crucifix form, right, through the middle of the column, and then put the column back together. So, moral of the story is that what I want you to do is just not specify through plate connections as your standard connection. Obviously, there are ways that are reasons why we would need to specify a through plate connection. You can't always get away with it. If it's used as a drag in your lateral system, so you're wanting to transfer axial load from one side of the column to the next, it's a very efficient way and a very efficient connection to do that with. So go ahead and specify it in that condition. Also, because our country is still split and we do, maybe on the eastern part, you don't always specify your own connection, in the western you typically do. If you get involved in designing someone else's connections, you might not have a choice. You might be stuck with a certain member size and having to design a connection that works for the loads and the members given to you. Obviously, in that type of situation, you might have to go with a through plate, so you might not have a choice. But bottom line, let's just try not to specify through plate connections. Using the A1085 material allows you to use a little bit thicker wall and a higher yield strength than you may be using right now, so that's going to get you a little bit more capacity, so we'll help with that matter with the through plates. All right, moving on to the next topic, which was moment connections. So again, I've got 4 moment connections that I'm going to show you that we discussed together. All 4 have about the same capacities. These are all non-pre-qualified connections that you would use in like a wind or a low seismic condition where you've got an R of 3 or less. And these are not in order of cost. I'll show you some cost input in a minute. So the first 2 would be more of a directly welded moment connection. So starting on the left, we've got the partial pen weld there. We've got a 5/8 inch wall that we're using for this column. This is actually going to be the most economical joint that I've come up with, but may not have all the capacity that you need. The CJP option is something that I've used in the past a bunch. Probably everybody's specified it, where you use a CJP weld to weld those flanges to the face of the tube. The next 2 are a through plate and a cutout plate option. So a through plate, these are shown just being one-sided connection. Of course, they're probably more often than not actually 2 sides. The through plate option is very labor intensive and fabricators despise it. Because if you can imagine, this through plate is actually passed through the column, just like the shear connection. For the plate for the top and the bottom flanges, you have to cut the column apart in order for this plate to pass through. It may pass through to a beam on the other side. You then have to weld all of these pieces back together. If you're doing it, I've shown it here as a splice location, because if you're doing it, you might as well go ahead and splice your column there if you need to. The other option is similar to a through plate, but maybe less labor intensive, and that would be the cutout plate option. So in this option, the plate actually wraps itself around the column and is welded to it. If it's two-sided, the plate will splice somewhere around the midpoint of the column and then can be welded to each side. These two options here, it may be hard to read, but we can actually get away with a thinner column for the design of these moment connections, and I could get away with a 3/8" column there. So kind of looking at the cost comparison, the relative costs, of course, vary. That's why I've just kind of given you ratios on a 1.0 scale, because costs on the East Coast versus costs on the West Coast versus a big fabricator versus a small fabricator versus, all the factors in between, they're all going to be different, of course. So just take that in mind when you're looking at this. This is just to give you an idea of relatively how they stack up to each other. So the PJP weld to the face of the column was going to be the least expensive. And you notice that I had to go with a thicker wall. That's all included in here. Is the material costs and the inspection costs are included with these fabrication costs that I built into this matrix. So with that PJP connection, even though I had to go with a 5/8" wall as compared to a 3/8 with some of the other connections, it's still going to be the least expensive. Notice also that the CJP weld, because of all of the testing that is required and extra fit up in the shop that's required to do this type of connection, it is going to be the most expensive. It's got a thicker wall and a lot more time required to do that type of connection. So it's going to be one of the two priciest. Obviously, it kind of makes sense that the through plate connection is the most expensive because of all the work involved in passing those plates through and then reconnecting the column up together, even though I can use a slightly thinner member. And then lastly, with a cutout plate connection, I can use a thinner member. It's still a little bit pricier, but maybe it's a better option if I need more strength than what I can get out of a PJP weld. All right, so moving on to trusses and types of welds when you're not just trusses, but if you're ever welding a tube to a tube together. So if we're using a tube beam to a column, some of these rules would apply as well. We would need to think about matched versus stepped connections. So matched connection is what every architect that you'll ever work with is going to demand. They're going to want. It's pretty, right? We've got an HSS branch member, HSS 6x6 branch member coming into an HSS 6x6 cord member, right? Fits up beautifully. The problem is that it's very hard to fabricate something like that and can cost money and can be hard for you to get the calculations to work as well. This really, when it comes to stepped and matched connections, really impacts the thicker tubes and the bigger tubes the most because of that radius that you see there on the corner on the left-hand side. So here it's not shown as bad, but if we get a thicker tube, then you're going to have a larger bending radius. The way that when they bend the tubes, if I've got it's 2 times, in general, it's 2 times the thickness of the tube. So a thicker tube is going to have a larger radius. Therefore, when that curve is bigger, when it comes to trying to fit that up, you may need some steel backing or some kind of weld backing in there that might be required to close that root of the joint in order to make that flare bevel weld there. In addition, flare bevel groove welds are relatively inefficient because of the limited effective throats that are allowed by AWS D11. You can pre-qualify and go through that work, but not a lot of people do. So what's best is really to try and get towards a stepped connection. Even if, and I might suggest that even if your client is requesting something with a matched connection, you might alert them to the benefits of going to a stepped connection. And what I mean by that is where I can get the branch members to actually land on the flat of the cord member or the continuous member. And the flat is just that, is that area away from the radius. It's defined as the width of the tube minus 4t. So there I can actually end up with a fillet weld, right? Connecting my branch member to my cord member. If I get some of the fillet weld that's going into the radius area, that's still okay. But if I talk to an architect and alert them to some of the benefits and the cost benefits to this, it may actually work out in your favor. For instance, if I'm putting together a truss that is going to be 40 feet in the air, are you really going to be able to tell if it's a match truss or a step truss? But it may end up saving the project thousands and thousands of dollars in fabrication costs, right? A really good example of this, I was just in Oklahoma City, or in Stillwater, but I flew in and out of Oklahoma City last week, I'm sorry, and I took a look at this bridge. This is a great example. So this bridge, it spans 380 feet, I believe, across I-40 in Oklahoma City. You fly under it going 80 miles an hour, right? Can anybody tell that it's a stepped or a matched connection? No, it looks matched. Looks beautiful, right? Only a crazy person like me crawls up the hill to try and get a great picture of it. But this is a perfect example. This is actually a stepped connection. The diagonal branch members are slightly narrower than the continuous chord member, but you would never be able to tell at 80 miles an hour going under there on I-40, right? So it's all about how, kind of like along the lines of AESS, if we are not going to see the truss, it's going to be 40 feet in the air, maybe you can get away with a step connection and save the project a bunch of fabrication costs in that respect. Trusses, the rule of thumb is minimum weight of the truss does not equal the least cost. And I would venture to expand this to a lot of things that apply to HSS, not just trusses, but a lot of member design, is that least weight is not going to always equal the least amount of cost. With HSS members, it's very hard to reinforce them. It's a little bit easier on some other members that you may use, but we can't just slap a stiffener on there and make all of our problems go away. So it is to your benefit to design your members, to think about your connection, and you might want to bump up your wall thickness a little bit more to make your connections a little bit easier. In addition, because these connections can be costly, you may think the Howe or the Pratt truss might be most economical because your members aren't spanning very far. Even though the members are going to span a little bit farther in the Warren truss, because of the number of connections goes down, that's actually going to be the most economical solution that you can have amongst those three. When you're sizing your weld for trusses, there are really a couple of options there. You can size to develop the yield strength of the branch member, of course, which is very conservative. It tends to hit that upper limit of a weld size, may be required in some instances. For instance, if you're designing something that is supporting moving loads, you might need to go ahead and develop the capacity of the member, but it's probably not the most economical solution there. Most economical and most preferred by fabricators would be to size to resist the actual applied load. So don't put on your drawings, size the members to meet the yield strength of the member or something like that I think was commonly done if you're not designing your own connection. And typically, as a rule of thumb, that if you properly design the members and the joint design, then hopefully an economical fillet weld is mostly what you will end up with if the members have been appropriately sized. This has a high impact on truss connections, obviously, because of the fabrication costs. The two options, gapped and overlap. So gapped is obviously the least expensive of the two options. It's nice because it leaves a little bit of tolerance in there when they're trying to fit up a truss. An overlap connection is obviously stronger, so structurally sometimes we depend on that. We will do an overlap connection when you've got large branch loads or we actually need to transfer loads between two branches. But the gap really gives the flexibility of fit up. So a lot of times in the shop, fabricators would like to tack weld their members together to make sure that everything's going to fit before they go through final welding. They obviously can't do that if they've got an overlap connection because they need to make a weld before they can come back and fit up the rest of the truss. So gapped connection is going to give us a little bit more economics in fabrication. When do we need to? I mentioned if there are high stresses or if we're trying to transfer load between these two. Also, if the components between the two branch members differ by more than 20%, then the more heavily loaded branch member needs to be the through member and welded all around. With an overlapped connection, there are also a couple different options of how you do it. If you're going to, I've seen architects want this type of detail. If you're going to do this where you've kind of got this bevel in two direction, that obviously adds because we're adding to the cutting that is required of the tube. But if you're going to do that, you really want to add this plate that you see in the middle. It's a little bit hard, my check mark moved a little bit. So you want to use A or B. Number C, where you're just welding them together, it's not going to develop the strength of an overlapping connection, and it's probably going to unnecessarily add huge costs because you can see you have very little flexibility in that connection. Round HSS for trusses can add 3 times the amount of cost to the connection. Whenever I think about round HSSs and trusses, I don't know why, but I always think of log rolling competitions and these little round members rolling around. So they are more expensive. Of course, they may be required or needed, but for a fabricator, they're harder to handle. You can imagine they're harder for them to lay out, harder for them to find the correct orientation. If they've marked it on one end, they have to make sure they can align it on the other end. So they're just a little bit more difficult and can also add to your fabrication costs. So if you have a choice, it might be better to specify a rectangular section. With all that being said, there is quite a bit of technology improvements in the tubular fabrication department that is helping and decreasing our cost, helping us decrease our cost. So one of those are these tube profiler laser cutting machines. And these are being purchased by fabricators, and I've also heard of them being purchased by regional service centers. So the service center could then offer to their client to do some of the cutting or the profiling of the tubes or the pipes. To be able to outsource that information or that kind of work, which would lead to everybody, more fabricators having more opportunities for these complicated projects that require maybe rounds especially or rectangles being profiled in 2 directions. Along with that, robotic welders are also coming into the world. They're used highly in Japan. These are actually Japanese pictures from Kobe Steel there. In Japanese construction, they actually use round HSS for most of their columns. I think I saw recently that they use them for 95% of their low to mid-rise construction. So they're used quite a bit. And they use them for their moment frames, as you're aware. I think they had an earthquake this morning, actually, that they have a lot of moment frame systems that were required to resist high earthquake loads. So for these moment frame systems, what you can see on the left-hand side is like a stub beam where they've actually used robots to weld all this together using a stub column. Then they'll weld those sections together in the shop and then fly it out to the site. And there they will connect the stub beams to an infill beam in between the 2 columns. We talked a little bit about PJP versus CJP welds. This concerning tube-to-tube connections. Obviously, PJP or partial joint penetration welds are a great option if your fillet welds become too large. So I would push your fillet welds up to maybe, if you can get up to a 1/2 inch, use a fillet weld. And then if you can't get that to work, then you can jump to a partial joint penetration weld. If you're welding tubes to tubes together and you specify a complete joint penetration weld, that requires, or without any backing, that requires a 6GR welding certification. It requires special fit up. And that may be okay if you are maybe, if the fabrication is being done in Houston or someplace along the Gulf where they do a lot of offshore work and they do a lot of those kinds of welds. But it's probably not the most economical thing to specify for the rest of the country. What I've found actually, and from talking to fabricators, is that sometimes the inspection on those welds just isn't done, or it's done inappropriately. So it's best to try and avoid, when we're specifying tube-to-tube connections, we want to avoid those complete joint penetrations, both for the difficulty and for the inspection. And just to give you an idea of what we're talking about cost-wise, is that for a tube-to-tube connection, a typical shop, if we've specified a fillet weld, it may take about 2 hours of fit-up for one guy to do in the shop, 2 hours. If we've specified a complete joint penetration weld of a tube-to-tube connection, it takes 1 to 1.5 days of fit-up for that same guy, Plus, obviously, the owner is incurring the inspection costs. So quite a bit of money is involved. And again, what may benefit this is by proper sizing of the tubes to begin with so that we can get a fillet weld to work. Welding end to end. So one of the fabricators brought this up, and I thought this was a good point because personally, as a starting out engineer, I didn't think about this when I've created connections. Obviously, this is a bit exaggerated, but if I'm having to weld two tubes together and they have different thicknesses, then you need to be aware that the radius, the corner radius, is going to be different because, as I stated earlier, the bending radius is dependent on the thickness of the tube. In addition, they're going to vary from producer to producer. So if you have one 8x8 by a quarter coming from one producer and an 8x8 by a quarter coming from another producer, and they happen to get mixed up in distribution or just along the way of their life, they could have slightly different radiuses if we're trying to weld together. So something you just need to be aware of and maybe take into account as you're specifying some connections, that you might want to do something that has a little bit more give in the connection, maybe two end plates together if you can, rather than just directly welding them together, which doesn't always give a lot of tolerance. And of course, if I'm doing two like are shown in this diagram that have two different thicknesses, then I may have a bigger, obviously this is exaggerated, but it's to illustrate the problem that I might have if I'm trying to weld them together. We'll get a great weld along the flat of the tube, but maybe no weld along the radius. Through bolting. So obviously, we can't just send our tubes down the same line that a wide flange is for bolt holes to be drilled. They may need to be manually drilled. There are lots of options besides through bolting, so there are many of them here actually for bolting two tubes. There are lots of products that are available, and you can see in the exposition hall. Bolt lengths for through bolts typically are going to exceed what's standard. So the standard bolt length that's stocked in every shop, we actually need something longer if we're going to ask it to go all the way through a tube, and so they may be a special order or maybe harder to get. Sometimes it's difficult to install. I'm sure those of you with young kids have tried installing different Legos or things where you're trying to get something through a hollow member. It can be a little bit difficult to install in the field. And if you do design it, then you need to treat it as a pin-type connection with the reduced bearing values that are specified in AISC 360. When it comes to the lengths of members, another thing that I heard from fabricators that they don't love about HSS is some of the waste. And some of this, as engineers, I don't know that we can really control. However, if we do work on jobs that have a lot of HSS, and if it's if you have some communication with a contractor, like if maybe you're in a design build or a design assist application, it may be beneficial for that contractor to go ahead and contact a mill that they will be producing tube from, because if a mill is selling their tube to a service center, they're typically going to sell in a certain length that the service center has requested. A little bit different than the way that they procure wide flange. So if you do have a lot of tubes, they can contact the mill and get a specific length that is required for your job, which may end up in a little bit less waste. So if you get a contractor asking for it, that's why. They're just trying to reduce the waste, and if you can give that type of information to them, they can pass it along to the mill and purchase exactly what they're looking for and reduce some of that. We also hear from fabricators, one of the big ticket items was the heartburn that they have with the number of sizes out there of tubes, and I'm sure you're well aware that there's a lot of different sizes that you can pick from, and as a practicing engineer, how do you know what's produced, what's readily available, what I can get, or I know as an engineer the last thing I want to hear from my fabricator is that, sorry, that size that you specified on your drawings, I can't find it anywhere. So you have to go back and redesign. So what the Steel Tube Institute has done to help you with that, both for engineers and fabricators, is develop this capability tool. So it really highlights the size ranges that are available in tubes. No longer are we stuck with, 8x8s being the biggest section available. You can go up to 22 squares and 7/8 inch walls. So there really is a very large range of sizes that you can pick from when sizing your HSS sections. This tool will help identify where you can get those actual sections. So on the capability tool that lives on our website, you can see I can specify, I missed a slide. I can specify what types of sections I want. So I can say that I'm looking for a specific range, or I'm looking for an 8x8 section, put that in the criteria. I can even reduce the sizes that are returned to me if I'm looking for need a seismically compact section. Once I do that and click search, then I get something like this that you see here with green, yellow, and dash marks. So I can go into the chart and I can find the section that I'm looking for. Once I find a section that I'm looking for, if it's green, that means that it's on one of our producers' rolling schedule. It means that they regularly make that section. If it's yellow, it means that the producer has the tooling to make that section, but they don't regularly roll it. It would be maybe like a 7x3 or 2 or something like that. So something that maybe people don't use as much, but if you need it for architectural reasons or need it for your job, then it's something that a producer could make. And then if you see something with a dash, that's probably something you want to stay away from. You can contact us at the Steel Tube Institute and we can help you. But that means that none of our producers have the tooling to produce that section. If I click on one of the sections that I see either green or yellow, then I'm going to see exactly who it is that produces that section. So if I want to pass that information on to a fabricator, if they're looking for a section, or if I am a fabricator and I need to pass it along to my service center so that they can go ahead and locate the section, I can do that. So hopefully a tool to help you identify which sections may be more prevalent in the marketplace than others. Oh, there's my search section. So this is the search screen. Sorry, it got lost in the shuffle. All right, architecturally exposed structural steel. There was a bit of conversation about that when it comes to fabrication. Obviously, we probably all have an idea of what it is, especially when it comes to tubes. It's specified a lot as AESS. And again, kind of like along the same lines as the matched versus step tube that I was talking about earlier. It all depends on how close you're going to be able to see the particular element on how you need to specify it. AESS falls under Section 10 of the Code of Standard Practice. It obviously has more restrictive fabrication erection tolerances, cleaner finishes, higher grade surface prep, tighter connection gaps, things like that. All of those great things are awesome for looking at, but they result in a higher cost premium. So make sure you're aware of what you're specifying when you specify something to be architecturally exposed structural steel. Obviously, not everything that's exposed needs to be that. If I am sticking a column in a target, I don't know that I would really need to specify that to be an architecturally exposed structural steel, but it would obviously depend on the proximity that you are to the element. HSS are used a lot, both because of their aesthetics, but also because they have a little bit tighter dimensional control. They're resistant to twisting when they're delivered and handled and erection, all of which is covered by the architecturally exposed structural steel spec, and therefore that's generally why it's used a little bit more. The flash weld on the outside of the HSS is always removed during production. If you need the flash weld on the inside of the tube removed, you need to specify that on your contract documents because it's not a default. That would need to be passed along to the mill when the shape is formed. Section 10.2.8 of the Code of Standard Practice states that the seams of HSS are acceptable as produced. So there's not really anything that we as producers would do differently to the seam weld, but obviously a fabricator is going to orient it away from view. That's what the Code of Standard Practice says. Going a step further, fabricators have indicated to me that if you as an engineer, or maybe, this is something you should talk about with an architect, if you have a highly architecturally sensitive tube in a location, maybe you want to discuss with your architect where you want that seam to be. Because the fabricator's idea of away from view may be different than the architect's idea of away from view. And you can specify that on your drawing so that the fabrication is done accordingly. The surface of an A53 pipe has a coating on it, so I know there probably are some people out there that are still specifying A53 for their round sections instead of A500. You really should switch to A500. You're going to get a higher yield. You're going to get a pipe that hasn't been hydrostatically tested, so it's probably going to be less expensive. And you're going to get a pipe that doesn't have to have a bunch of work done before it's fabricated. So because that coating is there, that has to be removed before any welding and surface prep is done. And if you have specified large tubular members that may not be covered under the A500 specification, they may have spiral welds. So you want to make sure that you check what you're getting when you specify any round sections that are getting up there in size, maybe above 16-inch diameter. These steel castings work really well for HSS in architecturally exposed situation. They're actually, the casting is sent to the fabrication shop and a complete joint penetration is done around. It's a very clean, very nice look if you're using those, if you need to use those for braces. That's a great connection to do if it's an architecturally exposed situation. Field welding usually requires, any temporary bolted erection aids, and they can be removed. I know that I am very guilty of putting that sentence on my drawings. Shame to admit it, but I did. All welds ground smooth for an architecturally exposed condition. Please don't put that on your drawings. I like to think that it's analogous to the tube-to-tube CJP. It just costs a ton of money, and really, I don't think that the product that you're going to end up with at the end is any better. It's going to cost a fabricator a lot of money, and the weld's going to look the same. It's kind of along those lines. So what the Code of Standard Practice actually says is a reasonably smooth and uniform weld, which probably is good enough for most AESS applications. Tolerances. This was probably the second biggest thing that I heard from my fabrication friends is that we as engineers need to have a better idea of what the tolerances are on these structures that we are specifying connections for, because I know I'm guilty of it. I kind of design in my little perfect world where everything is perfectly square, right? And there are no convex or concave walls, and my tubes are perfect, or my pipes are perfectly round. And I don't think about it, but we really need to think about it because HSS is no different than any other section that we deal with, and we need to leave a little bit of room in there if the walls aren't perfectly square. So HSS do have relatively tight tolerances. A lot of fabricators like dealing with them because of that, but there still are tolerances. And this is probably something that you need to pay more attention the larger the section that you get. So you got a 20 by 8 rectangular column, we need to think about how that might affect the connections that are going to be put together in the shop. So this is what A500 says on the left-hand side, the permissible variations, and it looks pretty small, right? There's a footnote that allows us to get larger tolerances for some of the larger rectangular shapes, and I've just done the math for you, and that's what's shown on the right-hand side there. So just to give you a real-world example of what we're talking about here, let's take a look at the HSS 12 by 4. So again, this diagram is greatly exaggerated. I hope you never see a tube like this. And we're not looking at large numbers here, but if we call for a connection when we've got two members like this, like an end plate connection that may have very little room for any of these tolerances, it might cause problems and adds costs on the fabrication side. So just running through the numbers real quick, for the small side, the ratio of the dimensions is 3 because it's a 12 by 4. So the tolerance is about 0.18 inches. So that section AA, going across the width of the tube, it can range from 4.18 to 3.82, and I've got those numbers slipped backwards, sorry. So pretty tight tolerances there. But now we look at the larger side, so that 12-inch dimension, or you can imagine if this is 24, then this would be double this. But the 12-inch dimension, the tolerance is actually 0.01 times the dimension, so in our case ends up being 0.12. So that dimension can actually range from 11.88 up to 12.12. Well, if I've got 12.12 on one end and I've got 12.12 on another end and I'm trying to connect something, I've got a 1/4 inch that I need to deal with, right? So something that we need to think about as engineers when we're detailing is that there may be some tolerances. And again, not something that we typically would have to deal with a shape like this, but if I'm getting into some of the larger sections that are now available for us. Similarly, for round sections, they may not always be perfectly round. So there is a tolerance that's specified for round sections of 0.75% when your outside diameter dimension exceeds 2 inches. So what that equates to for an 8-inch standard pipe, like I've got here, is that it can range from 8.56 up to 8.69. So again, probably not an issue if we're dealing with it on one end, but if we're dealing with a larger pipe or this type of similar condition on both ends, it may be a problem for the fabricator. There's also straightness tolerances, and for tubing, that equates to 1/8 of an inch for every 5 feet of length. Similarly, there are twist tolerances, and you can see those given here on the chart taken from A500. But really, when talking to fabricators, it was mostly that concave wall and convex wall that they wanted to share that can be an issue with some connections. I often get asked about rolling and curving members, and this is kind of a side note. I didn't have a fabricator specifically mention this to me, but I wanted to mention it because I think it goes well in it. And I get asked a lot about what are the capabilities, what are the rules of thumb that I should follow for rolling or curving members, and there really aren't rules of thumb because every roller has different capabilities. There are some that are very good at it and know how to do it really well and can bend at a very tight radius, and there are some that maybe you don't want to bend at a very tight radius or have done it less often, and so they don't have as much experience or the equipment necessary to bend at those tight of radiuses. And the thickness of the tube also depends on how that is performed. And so I ran across, this is from an old colleague of mine, this statement here that I thought was really good for engineers, and I'm sure there are contractors and fabricators and other people on the other side that roll their eyes at this and think this is horrible, but as an engineer, I think this is a good way of being able to cover ourselves if we need a thicker wall for rolling, because the fact of the matter is that as an engineer, I don't know who's going to roll the section. I know what I need for strength, but if I need a little bit more to get the radius that my architect is requesting, then I need the contractor to help me out with that. And I think this is a way of alerting the contractor so that they can help me out with that and the costs are covered. Of course, I always want to remind everybody, and I've alluded to this, that due to the flexibility of an HSS section, the local strength at the HSS at the connection may control the capacity of the connection. So we can't just design in a box where we typically would design all the members and then come back and design all of our connections. Or if I delegate my connections, I just design all of my members and think, oh, that's somebody else's problem. It's really the way to end up with the most efficient section is to think about the connections when you're designing the HSS member. And there is a tool that will help you do that. This does the checks that are specified in Chapter K. This is on the STI website. This is a great little tool for you to hop in as you're designing your members. It's not going to design everything for you, so it's not going to come up with weld sizes and bolts and things like that. But it will allow you to do a quick check of the member that you're designing to make sure that the walls are going to be okay. So we're not going to end up with through plates or other failures that I didn't expect or might be deal breakers when it comes back to me designing this connection later on. You may have been, remember HSS Connects when it was DOS-based, just me. Now it's obviously on the web and available for all to use. Just a quick note, then I'll take some questions about 1085. Hopefully you all have heard about it. I mentioned it earlier because you get a thicker wall with it. 1085 is a newer specification that's going to replace 8500 in the structural marketplace. The reason it has a thicker wall is because the wall tolerances are tighter. So that gives us that thicker wall. It also allows us to get rid of the 0.93 factor that's specified in B 4.1, I believe. It has one single yield strength, so regardless of the shape, you've got one yield, there's no grades. It's got a lower or a minimum yield strength of 50 KSI. It's got an upper bound of 70 KSI. What that's going to do by specifying that upper bound is the RY factor that we use in seismic capacity designs will come down. It also has a standard Sharpie V-notch test requirement, so if you need that for any maybe bridge type applications or other applications, 25 foot-pounds at 40 degrees Fahrenheit is standard for all the tubes that are produced for A1085. We have several producers making it right now. It's not in every service center across the nation, but it is starting to get out there in the marketplace, and if you specify it on your structural drawings now, you will be able to get it. So thanks for your time. There's my contact info. If you guys have any questions, please don't hesitate to stop by the booth or hang out here afterwards or send me an email later at a later date. And then I'll take some questions and I'll also put up the PDH code, which is 22731. 22731. Okay.
We have a question from the remote audience. Earlier when discussing connections, you didn't mention hollow bolts. Is there a problem when using them with HSS?
So the question was, earlier when I was mentioning bolts, I didn't, or talking about connections, I didn't specifically mention hollow bolts, because I was trying to stay generic and not mention a specific producer, but no, there's no problem with hollow bolts. It's a great option. There are lots of different types of bolts that you can use in hollow sections. Lindapter's hollow bolt is one, but there are several other manufacturers of bolts, that type of product that can be used as well. So. I'm sorry, can you repeat that? Yeah, there's probably, both HSS connections tend to lend themselves to welds because of the bolting, the lack of access to the inside of the tube. So field welding, or in any case that they can get away with doing it in the shop and then bolting in the field. Was that your question, or did I misunderstand it? Yes. Yeah, so I'm having trouble hearing you, I'm sorry, but if I understand you, yes. So a lot of what I showed can be done in the shop, but you're correct that a lot can be done in the field as well. Yes. Must be done in the field, can't be done in the shop. Yes. Is there a what for round? Cost difference? Cost. So the question is there a cost difference for round versus square? I would probably, I don't know off the top of my head. I would have to do a study to find out what the two equivalent sections are. Brad, do you know off the top of your head? Sorry, not to put you on the spot.
No, prices per pound. So
yeah.
It's not necessarily going to be, there could be a different size and the way of the material, but usually it costs per pound.
So for the same weight of section, it would be pretty the same?
Yeah.
So for the people remotely, Brad's answer was that the cost per pound is going to be the same for a round or a rectangle. So if I can get a more efficient round to work for the same height and the same load, then that would be the least expensive option. Yeah, that's for using A500 and A500. If we're comparing apples to apples, we're not bringing A53 into this. Yeah.
We have another question from the remote audience. For branch and cord members, if you still want to use a pipe section, is it still plausible to do that without a laser cutter?
Yes, very plausible to use. So the question was if we want to use round members in a truss, so we're connecting a round branch to a round cord members, can you do it without the plasma cutters? Absolutely. That's the way we've been doing it for years. So that's definitely doable.
Has there been any move to get the API file to provide AISC as opposed to just kind of moving outside of it? And similarly, has there been any move to also get some of the more advanced connection technologies adopted into AISC as well as kind of expanding on those some?
So the first question, has there been any move to have API 5L adopted into the AISC specification? And API 5L typically comes into our realm for large sections. That's why we end up going there. Jason or Brad, I haven't heard that that's come up. So I don't believe so. We can maybe discuss that later. The second question was about some of the CDECT, so the information that are in maybe like the CDEX design guides, getting those types of things into AISC's specification, correct? And I think that that's probably always up for discussion. There's probably more, I don't know if it's ever been brought up. I haven't sat on the specification committee long enough, but I can check on it, and maybe if you can leave me your card, then I will get back to you about it. Okay? Any other questions? Great, thanks for your time. Everybody have a good day.